Hello, and welcome to this eighth set of problems on complex numbers. In this set, we will solve problem number 71 to 80. So as I always say that you should pause the video when I state the problem and try to solve the problem yourself. If you cannot solve the problem yourself, only then look at the solution. The problem 71 says that for any two complex numbers Z1 and Z2, prove that mod of Z1 plus Z2 whole square is equal to mod of Z1 square plus mod of Z2 square plus 2 real of Z1 Z2 bar is equal to Z1 square plus Z2 square plus 2 real of Z1 bar Z2 bar. So if we substitute Z1 is equal to x1 plus iy1 and Z2 is equal to x2 plus iy2, we will get x1 square plus x2 square plus y1 square plus y2 square plus 2x1 x2 plus 2y1 y2. Now we can write this x1 square plus y1 square as mod of Z1 square, x2 square plus y2 square as mod of Z2 square, and then we will have 2 into x1 x2 plus y1 y2. Now we look at 2 real of Z1 Z2 bar, which will be equal to 2 real of x1 plus iy1 into x2 minus iy2. So this becomes x1 x2 plus y1 y2 minus I x1 y2 plus x2 y1. So the real part would be x1 x2 plus y1 y2, and we have 2 from here. So this is equal to this much. Similarly, we can prove that 2 real of Z1 bar Z2 bar Z1 bar into Z2 is equal to 2x1 x2 plus y1 y2, and thus we have proven the desired result. Problem 72 says that if Z1 mod of Z1 is equal to mod of Z2 is equal to 1, then prove that mod of Z1 plus Z2 is equal to mod of 1 by Z1 plus 1 by Z2. So right hand side is mod of 1 by Z1 plus 1 by Z2, so which is equal to mod of Z2 plus Z1 by Z1 Z2. Now we are given that mod of Z1 is equal to mod of Z2 is equal to 1, so mod of Z1 Z2 will be 1, and thus when we substitute this in the above equation over here, we will have mod of Z1 plus mod of Z2 is equal to 1 by mod of 1 by Z1 plus 1 by Z2. Problem 73 says that if mod of Z minus 2 is equal to 2 into mod of Z minus 1, then show that mod of Z square is equal to 4 by 3 real of Z. So we let Z is equal to x plus iy, then mod of Z minus 2 when squared will become x square minus 4x plus 4 plus y square, and twice of mod of Z minus 1 when squared will become 4x square minus 8x plus 4 plus 4y square. So on solving this, we get 3x square plus 3y square is equal to 4x. Now x square plus y square is mod of zx, and x is real of z. So we have 3 of mod z square is equal to 4 of real of z. So mod of z square is equal to 4 by 3 real of z. Problem 74 says that if cube root of a plus ib is equal to x plus iy, then prove that a by x plus b by y is equal to 4x square minus y square. So we have been given that cube root of a plus ib is equal to x plus iy, so we cube both sides. We get a plus ib is equal to x plus iy whole cube. Now you expand this, you will get x cube minus 3xy square plus I 3x square y minus y cube. Now we compare real and imaginary parts, so we get a is equal to x cube minus 3xy square and b is equal to 3x square y minus y cube. From this, we take x and we bring it to left hand side, we get a by x is equal to x square minus 3y square. And from this, we take y common and we bring to left hand side, we get b by y is equal to 3x square minus y square. You add both of these, you get a by x plus b by y is equal to 4x square minus y square. Problem 75 says that if x plus iy is equal to square root of a plus ib by c plus id, then prove that x square plus y square whole square is equal to a square plus b square by c square plus d square. So we square both sides, we get x plus iy whole square is equal to a plus ib by c plus id. You take mod of it, you get x plus iy whole square, mod of that is equal to mod of a plus ib by c plus id. Now this is equal to mod of a plus ib by mod of c plus id. You square both sides, you get x square plus y square whole square is equal to a square plus b square by c square plus d square. Square is missing over here for C. Problem 76 says that if z1, z2 up to zn are cube roots of, this should be nth root of unity, then prove that mod of zk is equal to mod of zk plus 1, where k belongs to 1 to n minus 1. So if z is equal to 1, that is cos 0 degree plus I sin 0 degree, which is equal to e to the power I2 or pi, where I is in natural numbers, then nth root of z will be e to the power I into 2 or pi by n. Now mod of this is 1, because there is no what you call modulus of this, that is modulus of this is 1. So when we have polar representation of a complex number z is equal to r into e to the power I theta, the modulus of e to the power I theta is 1 and the actual modulus of z will be r. Here r is 1, so mod of zk is equal to mod of zk plus 1 is equal to 1. Problem 77 says that if n is a positive integer greater than unity and z is a complex number, that is, find the equation z to the power n is equal to z plus 1 to the power n, then prove that real of z less than 0. The B is extra. It's a typing mistake. We are given that z to the power n is equal to z plus 1 to the power n. That is, z by z plus 1 is equal to 1 to the power 1 by n. Now, since it is an nth root of unity, we have just proven that mod of that would be 1. So mod of z is equal to mod of z plus 1. That when you square both sides, you will get x square plus y square is equal to x square plus 2x plus 1 plus y square, which means x is equal to minus half. So real of z is less than 0. We have to prove that in problem 78 that x to the power 3m plus x to the power 3n minus 1 plus x to the power 3r minus 2, where m and r are in set of natural numbers, is divisible by x square plus x plus 1. Roots of 1 plus x square would be omega and omega square. Now we let fx is equal to x to the power 3m plus x to the power 3n minus 1 plus x to the power 3n minus 2. So we have fx is equal to x to the power 3m plus x to the power 3n by x plus x to the power 3r by x square. We substitute omega for x. We get 1 plus 1 by omega plus 1 by omega square, because all these powers are multiple of 3. So when we substitute omega for x, it will become 1. Now we take LCM in this, we get 1 plus omega square by omega cube. This should be cube. Now 1 plus omega square is 0. So similarly, f of omega square is 0. So we see that f of x has same roots as 1 plus x square is equal to 0. So fx will be divisible by 1 plus x square. Problem 79 says that if square root of 3 plus I to the power n is equal to square root of 3 minus I to the power n, where n is a set of natural numbers, prove that the minimum value of n is 6. So we can write square root of 3 plus I as 2 into square root of 3 by 2 plus I into 1 by 2, which is 2 into cos pi by 6 plus I sin pi by 6. So we get 2 into e to the power I pi by 6. Similarly, square root of 3 minus I would be 2 to the power e to the power minus I pi by 6. So the imaginary part, that is the sign part, is preventing us from equality. So we need to get rid of this. So this happens at two places. Either this is 0 or it is multiple of pi. So to make it multiple of pi, we will have to multiply it with 6. That means this should be multiplied with 6. That means n will become 6. Problem 80 says that if square root of 3 minus I to the power n is equal to 2 to the power n, where n is in set of integers, prove that n is multiple of 12. So this is similar to previous problem. We have root 3 minus I is equal to the same 2 into cos pi by 6 minus I sin pi by 6. And then we are given that this is equal to 2 to the power n. So 2 to the power n will get cancelled. And what we have is cos n pi by 6 minus I sin pi by 6. This should be equal to 1. So the real part is 1 and imaginary part is 0. So n pi by 6, sine of n pi by 6 should be 0. That means n pi by 6 is equal to 2k pi, where k is a set of integers. So n is equal to 12k, which means n is multiple of 12. So with this, we come to the end of X set of problem on complex numbers. In the next set, we will solve 10 more problems and we'll continue till we end all the problems on complex numbers. I hope that you have enjoyed this video and found it useful. Please subscribe to the channel and like the video so that it can reach more students like yourself and benefit from it, because that's how YouTube algorithm works. The more the number of likes and the more the number of views and so on, the more is the chance of a video to appear in someone's search. Thanks a lot for watching. Enjoy.